In this video, we're going to begin a series of videos all about sensation and perception, the ways in which we sense and perceive. And I'm going to start this video by sort of contrasting between sensation and perception because these are two very different terms. They're related, but they refer to different sorts of processes in the brain. I will mention that this video will have quite a bit of terminology, and that's because we really need to set the foundation and the groundwork in order to get to the really interesting and exciting stuff in our next few videos, but I think this is pretty interesting as well, so let's jump right in. First of all, sensation. Sensation is the detection of physical energy, which by physical energy I simply mean mechanical energy, light particles, sound waves, things like that. So the detection of those sorts of things by our sense organs. What are our sense organs? Well, your ears, your eyes, your nose, your skin, your tongue, all of those different organs that map onto all of the senses that we have. So those sense organs then relay this information to the brain, turning the signal, that physical energy, into an electrical neuronal signal that the brain can actually use. Because remember, that's how communication in the brain works, by electrical activity in the neurons. And again, sensation is the process of taking that outside stuff, whatever it is, like sound waves or light particles, and turn it into something that your brain can communicate about. Perception is different. Perception is the brain's interpretation of sensation information. So this is the process of turning that electrical signal into a meaningful experience. As we'll learn about later when we get to vision, just to sort of spoil it a little bit and foreshadow, the way we see is not the way you experience sight. The way you sense the light particles from the outside world is very different. In fact, all of the images you get from the outside world when you open your eyes and see are upside down. And then it's your brain's job in the perception process to turn that image right side up. So the brain turns that relatively useless stuff, right, into that meaningful experience. And so what I'm going to focus on for the rest of this video is the principles that guide our ability to sense, starting with transduction, which I've hinted at already. Transduction is the process of converting that external energy or substance, that physical energy, mechanical energy, light particles, sound waves, the process of converting that stuff into electrical activity in the neurons using that sense receptor. So getting more specific, not just talking about sense organs, which is like your eye, right? Sense receptors are parts of these organs. So there are cells in the back of your eye that transduce light, just to use this term in a sentence. So it turns light particles into, again, electrical activity that the brain can use. We'll learn about this very soon when we get to vision. We'll talk about the retina and your rods and cones, again, just to foreshadow a little bit. You also have cells in part of your ear that transduce sound, and so on. Other principles, sensory adaptation. This is the idea that for all senses, activation is greatest when we first detect a stimulus, but then after that initial detection takes place, if we encounter that stimulus more or we're just in the presence of that stimulus for longer, activation tends to decrease. Now ask yourself, if you've watched any of my prior videos here, what does this remind you of? What does sensory adaptation remind you of? Well, if you said habituation, congratulations, gold star to you. That's right. It's basically habituation applied specifically to the realm of sensation and perception. Habituation states that, you respond the greatest to a stimulus upon first encounter with that stimulus. And then over time, over repeated exposure of that stimulus, your responses tend to decrease. Same sort of idea here, except at the level of the sense organs, sort of sensing stimuli from the outside world. Now, a lot of psychological research has gone into understanding and sort of evaluating the extent of our sensation and perception abilities. There's this whole field known as psychometrics looking at the ways in which we can sense and perceive. And so in terms of the limits of our perception, it's actually quite incredible. Here's an example, the absolute threshold. This is one metric for our sensation and perception abilities as human beings. The absolute threshold is simply the lowest level of a stimulus that we can detect 50% of the time when no other competing stimuli are present. So this is basically our ability to detect something at very, very low levels. And the question is, what's the lowest level of a stimulus we can reliably detect? Again, 50% of the time. Well, it's been shown that on a clear night, you can detect a single candle burning from 30 miles away. Humans can do that. Again, 50% of the time, that's the absolute threshold of light. It's also been shown in terms of smell that the absolute threshold of smell is 50 airborne particles, airborne molecules of a smell. We can detect that, which is pretty incredible because 50 molecules is not a lot of smell. Another metric, another interesting sort of quality of our perceptual ability is the just noticeable difference. This is the smallest change in the intensity of a stimulus that we can reliably detect. So, for example, can you notice the difference between an 80 decibel sound and an 81 decibel sound? If you can, great. Then we ask the next question. What about an 80 decibel sound versus an 80.5 decibel sound, right? And we keep going on from there. That's the just noticeable difference. Weber's law is sort of an application of these kinds of ideas, but it's an observation that takes it a step further. Weber's law is as follows. I'll state it and then I'll kind of explain an example because the definition might not be immediately clear. Weber's law states that the stronger the stimulus, the bigger the change needed for a change in stimulus intensity to be noticeable. So here's an example. Let's say you're operating a flashlight, okay? Now, on a clear night, that flashlight will produce lots of light. It'll be really useful. You'll get tons of light. You'll be able to see everything. You can light up environments far away, all of that good stuff. But if you were to take that same flashlight on a sunny day, it's not going to produce much light at all. In fact, that flashlight would be quite useless because there's strong stimulus, competing stimuli, already in the environment. On a bright day, the addition of some light is not going to be noticeable. That change in stimulus intensity, that additional light won't be noticeable. But in the absence, relative absence of light, on a clear night, on a dark night, an addition of just a little bit of light will be really noticeable. That's Weber's law. As a last sort of concept, a really interesting one, multimodality. Multiple modes, multiple senses. So multimodality is the principle which states that given the right circumstances, sensory systems, do not always stick to one sense. Here's a quick example. Have you ever rubbed your eye with your hand, right? Your eyes are closed, but you rub your eye. Well, if you do that, you'll notice that you produce the sensation, or the perception, I should say, of light. So even though your eyes are closed and no light particles are entering your eyeball, the sort of physical stimulus of your hands activate the sense receptors in the eye, giving a light response. I encourage you to do this, but do so relatively lightly. Don't hurt yourself, obviously, but it's a really interesting sort of phenomenon. And this illustrates, first of all, multimodality, that you're getting a different sense, light, in response to touch, right? So multiple modes, multiple senses. But it's also fascinating because it shows that sense receptors don't necessarily care what stimulates them. Your sense receptors in your eye, which I won't get too much into now until we get to vision, they don't care that I'm being activated by touch instead of light particles. They just say, oh, I'm active, okay, we're seeing light. Again, very interesting. One example, as a sort of final note in this video, one example of multimodality is synesthesia. Synesthesia is a rare condition in which people can hear or taste colors. They can see different numbers in different colors, and so on. There's different forms of synesthesia, but the point is it's an overlap of multiple sense modalities. So you might say to yourself, how the heck would we know that this is the case? Well, we can test it empirically. We can design experiments and studies to test this. Here's an example. You can show a slide like this to someone with synesthesia and someone without synesthesia. You can say, okay, on this slide, there are 5s, and there are 2s, the number 5 and the number 2. You could say, find the 2s. Okay, take a look. See if you can find the 2s. How many are you finding? How many are you seeing? How many are there total? Now, clearly you can do this task, but it's probably a little tough. You kind of got to scan all the different 5s. You got to look for the ones that are sort of flipped, the ones that are 2s. It might take you a minute to do, but you can do it reasonably well. For someone with synesthesia, the right kind of synesthesia, they'll do this in a split second because to them, it appears like this. They perceive 5s in a different color than the 2s, and so the 2s just pop out. If I were to give you a slide that looked like this in the very beginning, you would have got it in a split second too. But you don't have synesthesia, so it took you longer. This is a very interesting and fascinating and well-documented example of multimodality.